theory of evolution by natural selection. Charles Darwin's theory of evolution by natural selection is a revolutionary idea that explains the diversity of life on Earth. At its core, it's a beautifully simple concept with profound implications. The theory posits that all species of organisms arise and develop through the natural selection of small, inherited variations that increase the individual's ability to compete, survive, and reproduce. In other words, organisms best adapted to their environment are more likely to survive and pass on their genes. What makes this theory so powerful is its ability to explain the complexity of life without invoking any supernatural forces. It provides a mechanism for change over time, accounting for both the unity and diversity of life. From the intricate design of the human eye to the camouflage of a leaf insect, all can be explained through this lens. Darwin's theory not only revolutionized biology, but also profoundly impacted fields ranging from psychology to computer science. It changed our understanding of our place in the natural world, challenging long-held beliefs about the fixity of species and the special status of humans. Today, evolution by natural selection remains a cornerstone of modern biology, continuously reinforced by evidence from genetics, paleontology, and many other fields. It stands as a testament to the power of careful observation and logical reasoning in uncovering the fundamental truths of our world. Laws of motion and universal gravitation. Isaac Newton's laws of motion and universal gravitation represent a monumental leap in our understanding of the physical world. These laws provide a framework for describing the motion of objects and the forces acting upon them, from the fall of an apple to the orbits of planets. Newton's three laws of motion are deceptively simple yet incredibly powerful. The first law states that an object at rest stays at rest, and an object in motion stays in motion, unless acted upon by a force. The second law quantifies how a force changes the motion of an object. The third law states that for every action, there is an equal and opposite reaction. The law of universal gravitation extends these principles to explain the attractive force between all masses in the universe. It reveals that the same force causing an apple to fall also keeps the Moon in orbit around Earth and Earth around the Sun. These laws are profound in their universality. They apply equally to objects on Earth and celestial bodies, unifying terrestrial and celestial mechanics. This unification was revolutionary, suggesting that the entire universe operates under the same fundamental principles. Newton's work laid the foundation for classical mechanics and influenced fields far beyond physics. It provided a mathematical framework for the scientific revolution and shaped our modern understanding of the physical world. Even today, in the age of relativity and quantum mechanics, Newton's laws remain essential for describing much of our everyday world.
Click subscribe to this channel to get more topics you love.
Theory of general relativity. Albert Einstein's theory of general relativity is a profound reimagining of the nature of gravity, space, and time. It represents one of the most beautiful and elegant theories in all of science, describing gravity not as a force, but as a consequence of the curvature of space-time. At its heart, general relativity proposes that massive objects warp the fabric of space-time around them. This warping is what we experience as gravity. The theory paints a picture of the universe where space and time are not fixed and absolute, but dynamic and intertwined. One of the most striking aspects of general relativity is its predictive power. It accurately explained the precession of Mercury's orbit, which Newtonian physics couldn't account for. It also predicted phenomena like gravitational lensing and black holes, which were later observed and confirmed. The implications of general relativity extend far beyond gravity. It has profoundly impacted our understanding of the universe's structure and evolution. The theory forms the basis for modern cosmology, including our understanding of the Big Bang and the expansion of the universe. Perhaps most remarkably, general relativity has practical applications in our daily lives. The GPS systems we rely on for navigation must account for relativistic effects to maintain accuracy. This serves as a testament to the theory's precision and its relevance even a century after its formulation. Quantum mechanics. Quantum mechanics is a fundamental theory in physics that describes nature at the smallest scales of energy levels of atoms and subatomic particles. It's a realm where the intuitive rules of classical physics break down, revealing a bizarre and counterintuitive reality. At its core, quantum mechanics tells us that the physical properties of particles are not definite, but probabilistic. The famous Schrödinger's cat thought experiment illustrates this principle, where a cat in a box can be considered both alive and dead until observed. This concept, known as superposition, challenges our classical notions of reality. Another key principle is entanglement, where particles can become correlated in such a way that the quantum state of each particle cannot be described independently. Einstein famously referred to this as spooky action at a distance, highlighting its departure from classical physics. The implications of quantum mechanics are profound and far-reaching. It has not only revolutionized our understanding of the atomic and subatomic world, but also led to technological breakthroughs. Lasers, transistors, and magnetic resonance imaging (MRI) are just a few examples of technologies based on quantum principles. Perhaps most intriguingly, quantum mechanics hints at the fundamental nature of reality itself. It suggests a universe that is inherently probabilistic rather than deterministic, challenging our notions of causality and even the nature of existence. Despite its strangeness, quantum mechanics remains one of the most successful scientific theories, consistently validated by experiments. Discovery of DNA structure. The discovery of the structure of DNA deoxyribonucleic acid by James Watson, Francis Crick, Rosalind Franklin, and Maurice Wilkins is one of the most significant scientific breakthroughs of the 20th century. It unlocked the secret of how genetic information is stored, replicated, and transmitted in living organisms. The famous double helix structure of DNA, with its complementary base pairs, elegantly explains how genetic information can be copied and passed on. This structure allows for the stable storage of information, while also permitting easy access for replication and transcription. Understanding DNA's structure opened the floodgates for molecular biology and genetics. It provided the foundation for decoding the genetic code, understanding how genes are expressed, and how mutations can lead to diseases. This knowledge has revolutionized fields from medicine to agriculture, The impact of this discovery extends far beyond biology. It has profound implications for our understanding of evolution, offering insights into the relationships between species and the mechanisms of genetic change over time. It has also raised important ethical questions about genetic engineering and the nature of life itself. In the decades since its discovery, our understanding of DNA has led to remarkable technological advancements. From DNA fingerprinting in forensics to genetically modified crops in agriculture, from gene therapy in medicine to the possibility of resurrecting extinct species, the applications of this knowledge continue to expand and shape our world. Germ theory of disease. The germ theory of disease, developed primarily by Louis Pasteur and Robert Koch in the 19th century, represents a paradigm shift in our understanding of illness and health. This theory proposes that many diseases are caused by microorganisms too small to see without magnification, known as pathogens or germs. Before the germ theory, diseases were often attributed to spontaneous generation, bad air, or imbalances in bodily fluids. The idea that invisible living entities could cause illness was revolutionary and initially met with skepticism. However, through careful experimentation and observation, Pasteur, Koch, and others provided compelling evidence for this theory. The implications of the germ theory were profound and far-reaching. It led to the development of antiseptic and aseptic techniques in medicine, dramatically reducing mortality rates in hospitals. It spurred the creation of vaccines and antibiotics, allowing us to prevent and treat many infectious diseases that were once deadly. Beyond medicine, the germ theory had a significant impact on public health. It led to improvements in sanitation, water treatment, and food safety. The simple act of hand-washing, now understood as crucial for preventing disease spread, is a direct result of this theory. The germ theory continues to be foundational in modern medicine and microbiology. While we now know that not all diseases are caused by germs, and that the relationship between microorganisms and health is complex as in the human microbiome, the germ theory remains a cornerstone of our understanding of infectious diseases. Big Bang Theory. The Big Bang Theory is a profound and revolutionary model explaining the origin and evolution of our universe. It proposes that the universe began as an infinitely dense and hot singularity, which then rapidly expanded and cooled over billions of years to become the cosmos we observe today. This theory, first proposed by Georges Lemaitre and later developed by physicists like George Gamow and Ralph Alpha, provides a compelling explanation for several key observations. It accounts for the expansion of the universe, the cosmic microwave background radiation, and the abundance of light elements in the cosmos. One of the most mind-bending aspects of the Big Bang Theory is its implication that space and time themselves came into existence at the moment of the Big Bang. This challenges our intuitive notions of before and after as time as we understand. It didn't exist before the Big Bang. The theory has profound philosophical and theological implications, touching on questions of cosmic origins that have intrigued humanity for millennia. It has sparked debates about the nature of existence, the role of a potential creator, and our place in the universe. Despite its widespread acceptance, the Big Bang Theory still leaves some questions unanswered, such as what caused the initial singularity or what happened in the first fraction of a second after the Big Bang. These mysteries continue to drive research in cosmology and theoretical physics, pushing the boundaries of our understanding of the universe. Plate tectonics. The theory of plate tectonics is a unifying framework in Earth sciences that explains the large-scale motions of Earth's lithosphere. This theory, developed in the mid-20th century, revolutionized our understanding of Earth's geological processes and its long-term changes. At its core, plate tectonics proposes that Earth's outer shell is divided into several plates that glide over the rocky inner layer above the core. The interactions between these plates explain many geological phenomena, including the formation of mountains, oceanic trenches, the distribution of earthquakes, and the creation and destruction of landmasses. One of the most profound aspects of plate tectonics is its explanation of continental drift. The idea that continents move, once ridiculed, is now understood as a natural consequence of plate motion. This realization changed our perception of Earth from a static planet to a dynamic, ever-changing one. The theory of plate tectonics has far-reaching implications. It provides insights into climate change over geological timescales, the distribution of natural resources, and even the evolution of life. By understanding how continents have moved and collided over millions of years, we can better interpret the fossil record and the distribution of species. Perhaps most importantly, plate tectonics gives us a deeper appreciation of the interconnectedness of Earth's systems. It shows how processes deep within the Earth influence life on the surface, linking fields as diverse as geology, biology, and climatology in a grand, unified theory of how our planet works. Discovery of penicillin. The discovery of penicillin by Alexander Fleming in 1928 marks a pivotal moment in medical history, ushering in the age of antibiotics. This breakthrough transformed medicine, providing a powerful tool against bacterial infections that had previously been major causes of death. Fleming's discovery was famously serendipitous. He noticed that mold contaminating one of his Petri dishes had created a bacteria-free circle around itself. This observation led to the isolation of penicillin and the realization of its potential as an antibiotic. The impact of penicillin cannot be overstated. It saved countless lives during World War II and continues to be a crucial weapon against bacterial infections. Diseases that were once frequently fatal, such as pneumonia and scarlet fever, became treatable. This dramatically increased life expectancy and changed the landscape of public health. Beyond its direct medical applications, the discovery of penicillin spurred the development of other antibiotics. It opened up new fields of research in microbiology and pharmacology, leading to a deeper understanding of how drugs interact with biological systems. However, the success of antibiotics has also led to new challenges, particularly the rise of antibiotic-resistant bacteria. This ongoing issue underscores the importance of continued research and the need for responsible use of these powerful drugs. The story of penicillin thus continues to evolve, reminding us of both the power and the responsibility that come with scientific discovery. Atomic theory. The atomic theory, which posits that all matter is composed of small, indivisible particles called atoms, is one of the most fundamental concepts in science. Its development spans centuries, from ancient Greek philosophers to modern quantum physicists, each iteration bringing us closer to understanding the nature of matter. The modern atomic theory, largely developed in the 19th and early 20th centuries, reveals a world far more complex than early thinkers imagined. We now know that atoms, once thought indivisible, are composed of even smaller particles, protons, neutrons, and electrons. This understanding has allowed us to explain chemical reactions, radioactivity, and the periodic table of elements. One of the most profound aspects of atomic theory is its unification of the microscopic and macroscopic worlds. It explains how the properties of atoms determine the characteristics of the materials we interact with daily. From the conductivity of metals to the transparency of glass, atomic theory provides the underlying explanation. The implications of atomic theory extend far beyond chemistry and physics. It forms the basis for our understanding of nuclear energy, both its potential benefits and its dangers. It has led to technologies like electron microscopes and atomic clocks, and it underpins many medical diagnostic tools. Perhaps most philosophically intriguing is the realization that the seemingly solid world around us is mostly empty space, with tiny particles held together by fundamental forces. This view of reality, so different from our everyday experience, highlights the power of scientific inquiry to reveal the hidden nature of our universe. Laws of thermodynamics. The laws of thermodynamics are fundamental principles that govern the behavior of energy and its interactions with matter. These laws are universal, applying to systems ranging from subatomic particles to black holes, and they underpin much of our understanding of the physical world. The first law of thermodynamics, essentially a restatement of the conservation of energy, tells us that energy cannot be created or destroyed, only converted from one form to another. This principle is the foundation for understanding everything from the workings of a steam engine to the energy balance of the entire universe. The second law introduces the concept of entropy, often described as a measure of disorder in a system. It states that the total entropy of an isolated system always increases over time. This law explains why certain processes are irreversible and gives us the arrow of time. It has profound implications, suggesting that the universe tends towards a state of maximum entropy, often referred to as the heat death of the universe. The third law states that it's impossible to reach absolute zero temperature, providing a limit to how cold things can get. This has important implications for low-temperature physics and our understanding of material properties. Together, these laws provide a framework for understanding energy transformations, the efficiency of machines, and even the fate of the universe. They highlight the fundamental limits of what's possible in our universe, shaping our understanding of everything from everyday processes to cosmic phenomena. Discovery of X-rays. The discovery of X-rays by Wilhelm Conrad Röntgen in 1895 opened up a new world of possibilities in science and medicine. These high-energy electromagnetic waves, invisible to the human eye, allowed us to see inside objects and bodies without cutting them open, revolutionizing fields from medicine to materials science. Röntgen's discovery was accidental but momentous. While experimenting with cathode rays, he noticed that a nearby fluorescent screen glowed even when his apparatus was covered. He quickly realized he had discovered a new type of ray, which he called X-rays due to their unknown nature. The impact of X-rays on medicine was immediate and profound. For the first time, doctors could see inside the human body without surgery. This led to significant improvements in the diagnosis and treatment of conditions ranging from bone fractures to dental problems. The iconic X-ray image has become a symbol of medical technology. Beyond medicine, X-rays have become an invaluable tool in many fields. In astronomy, X-ray telescopes allow us to observe high-energy phenomena in the universe. In archaeology and art history, X-rays reveal hidden layers in paintings and artifacts. In security, they're used to scan luggage and cargo. The discovery of X-rays also paved the way for further exploration of the electromagnetic spectrum and contributed to the development of quantum physics. It stands as a testament to how an unexpected observation, in the hands of a curious and methodical scientist, can open up entirely new realms of knowledge and capability.